let's talk about examples for group 17. And group 17, they form, binary compound with hydrogen. Almost all elements form hydrogen compound. And they also form oxo compound and form oxo anion. So we'll talk about next slides, okay? And let's talk about hydrogen compound for this group. Then I think the most important property we need to pay attention is pKa. The reason is this hydrogen compound, that common acid. They are common mineral acid we use for labs in our daily studies and the chemistry labs. Okay, so you can say when you have this one has pK as 3.5 and HI that has -11. So if you remember the definition of pKa, we know when you have smaller value, that means that's a stronger. In this case, strongest EST acid in this row. Okay, that's strongest acid. Okay, acidity. Then hydrofluoride is the weakest acid in this theory. Okay, in this theory. If you look at the melting point and boiling point, we can say this one, if it's below 20 Celsius degree, so that's going to be a liquid, and all others they are gas. They're gas. Okay. Okay, so that's kind of the trend. And other thing, we don't have to pay too much attention to that. Okay. All right, let's talk about oxo anion compound using chlorine as example. So we have 4 oxo anion compound. This one is we have chlorine as +1 oxidation state. That's chlorine oxygen anion. That's called hyperchlorite. That's a neither. And then we have C infinity V geometry. That's point group. Okay, also indicating the geometry, linear structure. Okay, that's an oxidizing agent. And when you increase the oxidation state of chlorine, you can form chlorine O2 minus. That's chloride. Chloride. That's a C2V. Okay, that's like this structure. This type of structure. Okay, that's a anion. Okay, that's anion. But make sure you can write down the Lewis structure for this anion. Okay, Lewis structure. Lewis structure. Okay, for this anion. Okay, so make sure you can do that. Okay, then I think we have 2 lone pair here. Okay, then that's it. Okay. Then when you increase the oxidation state of chlorine, that become a stronger oxidant. Okay. So I'm not sure what's the disproportionation. Okay, but I can answer the question if someone asks the question. Okay, then when you go to +5, you have chlorate, you have C3V, and then that's also oxygen. Oxidizing agent, and +7 we get most common chloride oxo, and then that's perchlorate. Okay, that's a tetrahedral geometry. Okay, and that's also oxidizing agent, and also the this anion they tend to form ionic compound with hydrogen. Okay, they form chloride OX, and also they can form salt with cation like sodium. Okay, and for example, sodium chloroxide, that's the bleach active component for bleaching solution. Okay, because it has enough oxidizing capability to kill the bacteria and virus. Okay, we can use them to clean the house. Okay, and here's another class of the compound I want to introduce to you guys. So that's we call it interhalogen compound. So if you look at the name of this compound, that means the compound formed between, different halogen elements. Okay, we have example on the slides. So we have chloride fluoride compound, chloride trifluoride compound, chloride pentafluoride compound. Okay, and bromide, we have bromide fluoride, bromide trifluoride, and also we have, even this is dimer, it's I2Cl2. Okay, and hope you guys can draw the structure of this one. So look at this compound. Okay, look at this compound. Make sure you can use VSEPR, can draw the structure of this interhalogen compound. Okay, let's give an example. Okay, let's use chloride fluoride, right? So we have 5 fluoride, means we need to form 5 chloride bond, right? 5 fluoride bond, right? Then for chloride we will use 4 electrons for 5 electrons for each bond, right? Then we have 1 lone pair left, so we have this one. That's kind of say 4-way structure, or square planar structure. Okay, make sure you can draw structure of other ones. Okay, this one, that's a dimer. Think about how to draw this one. Okay, use the VSEPR principle. Okay, yeah. All right. Let's move on to the last group we're going to talk about in this lecture. So that's group 18. We call that inert group. The reason we call the inert group, because we have an S2 and Pu6 electronic configuration for all these elements. That's octet rule structure. Stable structure. So they just guess by themselves normally. These are very difficult to form compound, but they do form compound for some of them. We will talk about this one later. Okay. So we have helium, neon, and argon, krypton, xenon, and radon. Okay, radon. So this one, I just tell you a life story. Okay. Radon is a natural occurring gas, but it's toxic. It's a toxic gas. Okay, toxic gas, and it's commonly to see radon gas in Salt Lake City. Okay, so because especially in valley places, you can observe natural occurring radon gas. So whenever we build a house in Salt Lake area, and you have to use a detector or meter to test the level of radon gas. Make sure it's low enough to be safe for human being to live around. Okay, that's just a story about radon gas. Okay. All right. Here are some fundamental physical chemical properties of this group, and you can see in this group we don't have electronegativity data shown in this table. The reason is they don't form compound. Okay, we don't worry about the electronegativity for this group. Okay, they don't form compound. To correct, they don't form many compound. They only form for here, as I show you, only. I think before here they don't form compound, but here you start to form some simple compound. Not too many. They are very stable elements. Okay, but if you consider the stability of this group elements, okay, and if you look at the ionization energy, you see it tends to have large ionization energy compared to elements on the left side. Okay, that's nitrogen fluoride, nitrogen oxygen. Okay, So that's why, because they are stable. Okay, they hold the electron very tight. Okay, they hold the electron very tight. All right. So here are we said this group is very stable, not easy to form compound, right? But some of them, if you, for example, we are showing here exon, they do form compound with fluoride, oxide, and oxo fluoride. The reason is when you move top to the bottom, the electron for exon, they become floppy. They tend to become more reactive to form compound. Okay, but still, the whole group's relatively stable. Okay, relatively stable. And then you don't have form compound for argon, for neon, for helium, at least. Okay, at least. Okay, so we have the this one. That's a linear structure of accent difluoride, right? Accent difluoride. So the reason it adopts, this linear structure, because you can see it still have 3 lone pair occupy the equatorial plane. So the real structure, if you consider the lone pairs, they actually it's a, D3H, right? That's a trigonal bipyramidal structure, and here it's a square planar structure. Okay, square planar structure. So same thing. You need to use this principle. If I give the formula here, you should be able to draw the structure, including bond and lone pairs. Okay, like Lewis structure, and also tell the geometry of this compound. But this one, that's kind of kept the trigonal bipyramidal. That's kind of a little bit strange. Okay, and also we have exon O3, exon O4. And here, that's a what? That's a trigonal bipyramidal. That's D3H geometry. And here is square pyramidal. Okay, that's a C4V. Okay, that's cleaning up. No, that's cleaning up a little bit. That's not good. Okay, that's C4V. Okay, that's C4V. Okay. So that's there are some examples for exon to form fluoride, oxide, and oxo fluoride compound. Okay, and to end up these slides, I want to give you little additional information about group 18. Okay, group 18. So about helium and argon. Okay, and helium. Okay, helium. We found common use of these two gas molecule, two inert gas in chemistry lab. Okay, so this we use for AMR, and AMR you guys use a lot, right? So the reason we use it for AMR, because helium is a cooling gas. When it's liquid, it's very cool gas, a cool liquid. So we use this cooling to stabilize the superconductor in AMR instrument. It make the superconductivity and the magnetic field stable. We have to use this helium gas, and that's very common. Okay, and argon we also use that for lab. We use that as a control gas atmosphere. Because argon does not react with any compound. So when you run a reaction under argon, it's perfectly stable. So the gas won't react with your reaction. Okay, when interact. Okay. So another common gas we use as a control gas is nitrogen, but nitrogen is not good as argon. But nitrogen is still react with some compound, like it react with decent. Okay, but this one is good. I think that's some little additional information I want to share with you about group 18. Even though like this helium argon, they don't react, right? They don't form compound, but we still found the important applications in our chemistry insights. Okay, all right, and I think I'm going to end up this lecture, and I look forward to see you guys next Tuesday, and watch this next video by yourself, and then we are going to I'm going to answer any question you may have for this lecture. Okay, I will give you a few minutes to address any question you may have. Okay, all right, see you next Tuesday.